In this video, we're going to be working through an example problem to help convince us that substitution for atoms really works, using the formula P or not Q implies P or not Q. We will use truth tables to try to convince us that substitution for atoms really works. Right away, we see the root node of this formula is implies. So we see that the formula is of the form A implies A, which means when it comes to truth tables, we'll also need a formula of the form P implies P. So let's draw a truth table of P implies P first. We have just one atom, P, and the formula P implies P. So the truth table works out to be quite simple. And we see from this truth table that P implies P is indeed valid. If we then draw a truth table for A implies A, it's similar. We have A, and A implies A, and just two lines of truth table. And we see again that A implies A works out to be valid. Pause the video for a moment and try to answer for yourself why we might do something so seemingly redundant as to draw a truth table for both P implies P and A implies A. Were you able to think of anything? Okay, let's move on and evaluate the whole formula, just to make sure that the substitution for atoms approach seems to be working. So we draw a truth table for P or not Q implies P or not Q. And if we fill in this truth table, we see that this formula is indeed valid. So substitution for atoms does seem to be reliable. But why might we do something so silly as to have a truth table for P implies P and a truth table for A implies A? Well, if you remember, P implies P lives in the object language. And A implies A lives in the observer language. But still, why might this be useful for us? Well, our formula can be factored into the form A implies A. A implies A lives in the meta-language, so we look to P implies P in the object language, in the language of logic itself, for what the truth table of an A implies A might be. That's why we care about both of them, because our formula doesn't factor into P implies P. It only factors into A implies A. But A implies A doesn't strictly have a truth table on its own, only P implies P does. However, there's a direct relationship between the truth table for P implies P and the truth table for anything of the form A implies A. So that's why we care about using two separate formulas with two separate truth tables. One is in the object language and one is in the observer language. A formula can be factored or represented in the observer language more generally in a form such as A implies A. But A implies A relies on the truth table from P implies P. This is why substitution for atoms works, because a formula like the one we have here can be factored into a formula in the meta-language like A implies A, which can then gain a truth table from a formula in the object language like P implies P, verifying that the form is valid. Try summarizing this to yourself in your own words.